In this video, I'm going to go over some of the read slope area information in a little bit more detail. So this is going to be specifically about finding information from graphs. So in AP Physics 1, when we use equations, most of these equations are only valid in certain situations. And those situations usually have to do with certain variables being constant. For example, all of the kinematics equations that we've done so far require a constant acceleration. If the acceleration is changing, you cannot use these equations. And really, this is the difference between algebra-based physics and calculus-based physics. The kinematics equations require constant acceleration. If we have a changing acceleration, then we need to do calculus. Now, the same is true of the net force equation. If you have a changing acceleration, the equation doesn't work, and you would have to use calculus. Another example would be constant force. If you have a changing force, then the impulse momentum equation and the Newton's second law equation, again, don't work. They require a constant force, not a changing force. So if we have a non-constant force, a non-constant acceleration, then that's going to require us in AP Physics 1 to get our information from graphs, whether that's the slope or it's the area. So I'm going to go through specifically what information you can get from read, slope, and area on a graph. There's a couple of specific bits of wording that we hadn't used yet, so I'm going to cover them here. So first, let's talk about read. When we read information from a graph, we are finding whatever the y-axis variable is when the x-axis variable equals a specific amount. So for example, right at this location here, the speed is 20 meters per second when the time is 2 seconds. This is called the instantaneous velocity. It is the velocity at that instant. If I look anywhere before or after, the velocity is going to be different. Remember, speed and velocity right now are essentially the same thing. Now, with this graph, the force versus time graph, we can do the same thing. At this location, the net force is 20 newtons at a time of 2 seconds. Again, this is the instantaneous force. This is the force at 2 seconds. But before that and after that, the force is going to be different. So when we do read slope area, yes, you do need to write down what you can read off the graph. On the assignment you're going to be working on, there are problems where you have to get information just by reading the graph. It's not unheard of, and you do have to remember that you can read the force at t equals 4 seconds, or the velocity at t equals 3 seconds, or two different forces or velocity to find the change in. So just remember, read the graph is important. All right, slope. The slope tells us the rate of change of whatever your y-axis variable is per unit of change of the x-axis variable. So far, everything we've been doing with x-axis has had time on the x-axis. So when we're talking about the slope of a velocity versus time graph, we're talking about the change in velocity per second, because the unit of time is a second. So it's the change in velocity per second, or per unit of time. So whenever I want to know what the slope was going to tell me, remember, slope is rise over run, or you could say it is the change in the y variable divided by the change in the x variable. Well, if I look at this graph, I have speed is my y variable. So that would be change in velocity over my x variable is the change in time. So this is the base of the equation that I could use to find the slope of this graph. And what I need to do is I need to match that to one of my equations. I need to see if there's any equation that I could turn into change in velocity over time, because that will tell me what the slope is equal to. So the equation this actually matches to is this one. And I think on your notes, this might say A equals. It should just be V, or this is specifically V final. So is there a way to turn this into delta V divided by delta T? Well, yes. If I subtract the initial velocity from both sides, I get my final velocity minus my initial velocity is acceleration times time. And then I'm going to divide both sides by time. And final minus initial is equal to delta v divided by t, and that is equal to the acceleration. So the slope is the acceleration. And if you notice, the slope here is not changing, it is constant. The slope is the same everywhere. Now the last thing we can do is we can find the area. And the area is a little bit more complicated. When we have a constant or horizontal slope, then the area is the area of basically a square or rectangle. And it's going to be whatever variable you have on the height times the base. So we would have force times time. And so I'm going to take that and see if I can match it to any of our equations, and it equals delta P. So this is part of our impulse momentum equation, but the change in momentum is equal to the force times time. So the area is force times time. Now, usually when we find the area, we have a slope that is not horizontal. So to determine what the area tells you, you still match the equation as if it is. You just do your y-axis times your x-axis, and then find out what that matches. But to find the number, you have to do the area of the shape. So for example, with this one, it's our triangle. So the area would be 1/2 the force times time, the height times the base. So that area is still going to tell you the delta P, but since the force isn't constant, the slope, the fact that it's a triangle instead of a square, is what accounts for a non-constant force. So also be aware that whenever you're finding the area, you're not finding the momentum. You're finding the change in the momentum. If this was a velocity versus time graph, you wouldn't be finding the position, you would be finding the change in position, which is delta x. So whenever you're looking at the area, you're usually looking at the change in. And one of the graphs on your assignment does have a different graph than what we've done before, and you'll be finding the area, which is the change in something. So for any of those of you who have who are taking calculus, this is how this whole thing works. Whenever we're getting those slopes, those are our derivatives, our areas are our integrals. And if we have changing velocities, changing forces, we really need to use calculus, but we're not doing that. All right, so on your assignment, there is this quick start. It's at the top, but I went through the notes first. Now I would like you to pause the video, take some time, and try and figuring out the slope and area for each of these graphs. What do they mean? Some of them you might have to manipulate the equation a little bit to get it to match, but not all of them. And graph A has both a slope and an area that means something. B, C, and D, it's either the slope or the area. So go ahead and stop, and then I will go through the answer just so that you can make sure you understand what's happening. Okay, so for graph A, remember this is a velocity versus time. So for slope, I do my change in velocity divided by time. And that one is pretty obviously, well, it's going to match with this one. Change in velocity over time is acceleration. But this is the way that the equation looks on the formula chart. So yes, you would have to know that final minus initial is delta V divided by T is A. You need to know how to do that manipulation to correctly match them. For the area, I'm going to do my velocity times time. So it's velocity times time. And I need to know if any of these equations match that. So velocity times time would match with this equation. I can multiply both sides by t, and velocity times time is going to be delta x. Delta x is our displacement. All right, looking at the next graph, position versus time. So the slope is change in position, which is delta x, divided by t, and that matches with this one. So it's going to be equal to velocity. For area, this is position times time. But looking at all these equations, there's no way to get a position times time. So this one doesn't mean anything. All right, for graph C, we have net force and time. So force divided by time, or delta F divided by time. And our only one we have is here that has force in it. And this is not force divided by time, so this one doesn't have a meaning. But the area is force times time. So the area is going to give us our change in momentum. For the acceleration times time, our slope is acceleration divided by time. And looking at all of these are the only ones that have acceleration in them. So I can do acceleration times time, like this, but I can't do acceleration divided by time. So this is meaningless to us. But acceleration times time is equal to our change in velocity. So we actually have enough information just in this quick start to allow you to do your read slope area for all of the graphs on the assignment. So do the best you can and try and work through them as much as possible.